Shifa, and today I will explain my part of this assignment, that is question 1, the difference between binary tree and a tree, and difference between pre-order, post-order, and in-order. I'm sorry for not showing my face. I have some issue with my webcam. So binary tree and general tree has obvious difference between them. Tree can have multiple number of child, while binary tree can only have 2 child. General tree or a tree can have more than 2 child. For example, from this graph, you can see that this is an example of a general tree where its root have more than 2 child, while in binary tree can only have 2 child. Okay, so general tree does not have any sort of order. The value can be placed anywhere while in binary tree, the value have some sort of order. For example, maybe in the left subtree, the value must be less than the number in the root, while in the subtree, the number must be larger than the number in the root. The next part is the difference between pre-order, in-order, and post-order. So pre-order traversal start from the root to the right and to the left, and in-order traversal start from the left and to the root and to the right. And lastly, for the post-order, traversal start from the left to the right, and to the root. I will explain the pre-order part on how it works. For pre-order, the rule is to start with the root, right and left. So starting with the root here, in the blue circle, start with the root is 45. We put on 45. The right is 40. But we must start with the root. So going on into the green circle, the root is 35. And then we move on to the right part. That is 26. And then next step we can move to the left, which is 36. And then going into the orange circle, still on the left part, that is 41. We already put on the root, so it is the right we already cover, and then we have to cover the left circle, which is here in the orange circle. Starting with the root is 52. So and then going to the right is 51, and going to the left is 54. So that is the end of pre-order. That is pre-order traversal. Okay, so in-order traversal rules is to start with the left, root, and the right. So for this tree, start with the left, which is in this green circle. The left node is 2, so we put on 2, the root 3, and the right 4. And then moving on to the orange circle, that is the left is 3. We already put on 3, so we can skip that and go to the root, which is 6, and to the right 7. And then moving on to the blue, we cannot put on root yet. We have to go to the right. We already put on the 6 for the left. So the right is 14. Put on 14. For the right is 14, but the 14 has child. So read from the left, 13. So put 13. Root 14, and the right is 16. So that is for the in-order traversal. For post-order, the rules are to start with the left, and then right, and then root. So I draw the circle same as the previous tree. To make it easier, we start from the left, which is here. The node 9. So we put on 9. And then the right is in this circle is 13. So we put on 13. And then the root is 11. So we put on 11. And then we can't go to 19 yet because it is the root. So we have to move on to the right side, which is this step is the right side. The right side of this is the right side of this subtree start with the left one is 22, so round 2. And then going to the right, 27, and the root, 24. And then after finishing both of these green circles, we can move to the blue circle. So that is the one.
The second question is, what are the benefits of binary search tree and what are some use cases in modern science computer world? The benefits of binary search tree are lookups can be done in logarithmic time, which matters a lot when n, which is number of nodes in the tree, is large. The second is anytime we need to traverse the increasing or decreasing order of keys, we just need to do the in order or reverse in order traversal on the tree. The third one is can implement order statistics with binary search tree because it is possible to look at the data structure as a sorted array. The fourth one is can be used in design of memory allocators to speed up search of free blocks and to implement best fit algorithms where we are interested in finding the smallest free chunk with size greater than or equal to size specified in allocation request. Some of the uses of binary search tree are search application where data is entering or leaving, such as the map and set object in languages libraries. The second one is Huffman coding. Huffman coding is a method of compression that is independent of the data type, where the data could represent an image, audio, or spreadsheet.
Assalamualaikum and hello. My name is Iskandar Musa. So now I will be explaining what is heuristic search. Heuristic search is a process to optimize a problem using heuristic function. Heuristic function will calculate and gives estimation on the cost of start node to goal node, and the lowest cost node will be selected from the possible choices. There are two search techniques available. The first technique is uninformed search, or you could call it direct heuristic search. Uninformed search is not always possible because it requires much time or memory. This is because it searches the entire state space for a solution, or in other words, it operates in a brute force way. The example for uninformed search is breadth first search and depth first search. The second technique is informed search or weak heuristic search. Most of the time when you search for heuristic search, informed search will come out because it makes use of heuristic function I mean. This is because unlike uninformed search, the informed search has information about the estimated distance between the current state to the goal state. So that is why uninformed search takes a longer time and more memory because it searches the entire space to find the solution. The example for informed search is best first search, A-star search, hill climbing, and more. Now, moving on to A-star search. A-star search is one of the best algorithms that is based on heuristic methods, which achieves optimality and completeness. And so, how does it work? Imagine you are using Waze or Google Maps and you are trying to get from Perak to Pahang. It can go through a lot of different routes and it will take some time to reach each checkpoint. Then it will calculate which route can get you from Perak to Pahang the quickest. An example of how other graph traversal algorithms works, it will go through each one of the nodes to get from point A to point B. While on the other hand, A-star search will find a shortcut to get from point A to point B. So for example, you want to get from node A to node D. Which path will reach the node D the quickest? There's A to D, which costs a total of 7, A to B to D, which costs a total of 6, or A to C, which costs a total of 15. The obvious answer will be A to B to D. With a total of 6, it has the shortest path among other paths.
Okay, Assalamualaikum. Hello, my name is Muhammad Failuman. I will present the section B part, which is about me by using breadth-first search, or we call it as BFF, a search or traversing algorithm where we use in this maze application. We want to find the possible path from the starting point to endpoint, which is this. The X here symbolizes the endpoint, the 0 symbolizes the starting point. So we will use this breadth-first search along with Q will help to keep track and store possible path that we will visit later on once we're done with this path. As we know, Q applies the concept of FIFO, first in, first out. So it reflects the real life scenario of Q, the first one to Q, the first one to out. So I'm going to demonstrate first the output of it. So basically I have like 4 maze. Maybe I'm just going to show you like 3 or 2. So create maze 1. So this is the first maze that I'm going to show example. So we see this is the starting point and this is the end point, which is here. With the help of breadth-first search and Q, we can find the possible path and most importantly the shortest path. For this one, we can see there's only one possible path because there's a wall here which restricts our movement. However, okay, I'm going to show you the second example. So this is the second example. As you can see, actually there's 2 possible paths. The first path is this one, which is what the system assigned. Okay, this is considered the shortest path out of 2 paths. Now, as you can see here, we can calculate 1, 2, 3, 4, 5, 6. Try the alternative, which is this 1, 2, 3, 4, 5, 6, 7, 8. So there's like 8 steps we need, while this one only needs 6 steps, the optimal one. So this is what breadth-first search can do. I'm gonna show you on the implementation part on how it's done. Okay, I'm gonna use the create maze 4. This one is much more simpler. If I use the other one, the one that I show you, it's more large and require a lot of loopings and stuff. We're gonna debug it. Okay, so this is the simple one. This function, what it does is to create the maze, and as you can see, we use list. It's a 2D list. It's more like an agency matrix. For example, how we want to determine the x, just like any other array. This is the x-axis, the I, we call it I. This is the j, the y-axis. So to get the x value, okay, for the j, it have to be 2 at index position 2. And for the I, it has to be at index position 1. To get to the x value, you need to have 2 and 1. Okay, this one is to print the maze. We will use at the output. Basically, once we already find the endpoint, which is here, we're going to display the maze with a possible path. And then we also have other methods such as validate. This method is, the function is to validate whether the path that we go is a clear path or a wall. A wall is something like this, the hashtag one. We also have the negative, okay, this outside, we also don't want that. This method will validate with 2 if-else conditions. First condition is if it's less than 0 or more than the length of the array, means that it's outside the boundary of the array. So we will return false, invalid path. So we should not store it in our queue, because queue we store only possible paths to get to our goal. This one, this is what I explained before. We use this j and I to get to the position, the index position, to know the value of the index position. So for this, if the value is a hashtag, which means mob, so we have its invalid path, we return false. We cannot use it. If not, it return true. Okay, so this is the method of find and it's going to validate whether we have reached the endpoint or not. If it's endpoint, then obviously we're going to like display the maze and all. We're going to stop the loop. The condition is just like the wall. So if the value is x, we know that the position that we are in right now is x. We know that this is the endpoint, so we're gonna print it and we return true. So that means the while loop will break. Else we return false, means the loop will continue to looping again and again until we reach the endpoint. So now I'm gonna show you how basically implementation work. Okay, so this is the main algorithm part where it shows the overall flow of how this breadth-first search along with queue works. Okay, so first we create the queue. Then secondly, this dot put. Okay, this queue name is nonce, and by using queue we can have a method called dot put, which is the put method is to insert any elements that we want to insert in the queue. It could be numbers, strings, and then this add variable is for us to validate. By using this add variable to validate the move with the left, right, or down is actually the path, the end path to the endpoint. Okay, the final path to the endpoint. We want to validate that. So we use this method, and this while not find in means that if we did not find the endpoint yet, that means we have to run everything in the while statement here. Everything repeatedly. Once it will stop once we already find the end, which is the endpoint. So if it did not, then we run it. So let's say here, first we put on our blank string. It start with blank string, which is okay. Later we combine it with our own specific left, right, up, and down. So okay, it's going to check here whether the blank string is the endpoint, which is obviously is not the endpoint. Okay, we inside the find end method, and this loop is just to get the starting position. Okay, so that later on we can move our we can move to the left or right, okay, by altering the index position value. But then this is blank string, so we're not going to move it anywhere. And we also want to check, okay, since this is find end method, we want to check whether the value that we access right now is actually x, which is the endpoint. So it's not, as I said before. So return false. So we're going to go through the statement inside the while loop. So first we're going to retrieve our actually the blank string is inside the queue because we put it here, but then we're going to retrieve it and put it in our add variable. So then we're going to run, and there's this for loop cycle, okay, where it's going to run since we are talking about breadth-first search, we're going to run every single possible path. So left, right, up, and down, it will be run. So this loop will run 4 times every single, so basically we will combine it with our variable add. Okay, for now it's a string, but let's say if our variable right now it's d, okay, d you can combine with j. Let's say our first loop cycle is l, so we're going to like dl, and then second loop cycle dr, du, dd, and then so on, like ddr, ddl. We're going to get every single possible path for it. And of course, just having every single possible path is not okay. I mean, like, we also have to like filter it out, validate it, whether that path is actually a wall or a clear path, like this one, a wall, clear path, or outside of the mains. So this method is used, which I already explained earlier. So let's say if it's a valid, then we're going to enqueue it into our queue. When we enqueue those elements into our queue, that means that path means that we're going to visit it after this. Okay, let's say we have 4 paths in our queue. That 4 paths will be visited. We will visit that 4 paths. So we don't want to visit path with a wall path or invalid path. So we don't, if it's not valid, we don't put it in our queue here. But if it's valid, we enqueue it into our queue. So for now, the blank string is not valid, obviously. So we're not gonna put it into our queue. So then basically we're going to loop based on, since I said L and the string, if we combine it become L, and then if we combine R, it's become R. So it's going to validate whether L and R is in the is a valid path or not. As we can see, L is not a valid path. Why is that? Because you see, from this starting point, if we go left, it's a wall. If we go right, it's a wall. So it's both are not valid path. How about U? So U, if we go from here to up, it's also not a valid path because it's outside of our maze. How about D? D, if we go down, it's a valid path. So we're gonna store that for sure. So I'm just gonna skip this over. So this is the D part. Okay, see, it's written through, means it's a valid path. So we're gonna include it. So now we have D in our queue. You see? Then we're going to, okay, this one we're going to see again to find n, whether it's currently our add is the blank string. So yeah, basically it's not the endpoint. So I'm just gonna skip it. It's gonna run the loop again. So we're gonna get the new element from the queue, which is the D. So we replace it with our string. So now we're gonna do the similar thing where D will combine with the L, R, U, and D. So for like the L means down left, it's invalid, down right invalid, down down, and down up. Down up is actually not invalid. I mean it's actually valid down up, because why? It's actually a possible path because it's not a wall, it's not outside of the maze, but it's not the shortest path because we go up and then we go down back. So yeah, but still it's a possible path. So we actually can take it. Okay, we can take this. So still acceptable. And then we have like DD. DD is also a possible path. So I'm going to show you through this debugger. Right now we are at, see the L, we add the L, and we're going to return false. See, return false. Okay, now we're going to go the R. You see the R, also going to return false. I'm just going to skip it because it's too much. And then we have DU. Okay, DU actually, as I see, is a valid path. And that is breadth search. That's what breadth search is. Breadth first search is. It's going to find every possible path. But it's a, you know. So you see, it's true. And so on with the D. Okay, so we include. So as you can see, we already have two Q. I can show you the proof here. We have two Q. See, DU and DD, same as this. Okay, so now we're gonna check whether our add, which is at the moment is D, is endpoint or not, which obviously is not the endpoint because D is at here. So it's not an endpoint. I'm just gonna skip it again. Return false. Now we're going to get our next Q element, and for the existing one, just here. Okay, we're gonna replace it with our previous, and so now it's DU. Again, we're going to do the same thing, the DUL, which means down, up, left, invalid, down, up, right, invalid, down, up, down is actually not invalid. It's possible, but it's not the shortest path. So, but still we need to put it. I'm gonna put it. Let me put it down, up, down. We're gonna see later. I'm gonna show you. For now, it's down, down, up, up. Okay, down, up, down. As you can see, we'll return true. See, it returned true. So now it's valid, it's going to incubate. So as you can see in our queue now, we have two, DD and DUD. So yeah, I'm just going to explain it here more faster than this one. Okay, so right now, we already have this. We're going to check whether DU is the endpoint, which is not true. So what we're going to do next is, as according to the loops, we're going to replace it with our DD. We know that DD is actually the endpoint because from here, starting down and down, this is the endpoint. However, we still have to run the code here because to reach this part, we have to run first here, and then we go back here, and then we validate the DD. because the previous one they validated the add outside of the while loop, which we did not retrieve yet the queue. So yeah, we're gonna do, even though we know that we won't need it, but still we're gonna run. And DD down is not valid, DD right, left not valid, DD up actually valid. It's actually valid. And we're still gonna put it, even though we know that we won't run it, because we know that DD is the fastest, the shortest path. So, but still we put it. So I'm just gonna skip it just to show you the output, which is similar to what I'm talking about right now. So now DD right, okay, this is DD out. So it's gonna return true. See, it's written true, and then we queue it. And then now, okay, DD down is obviously invalid. I'm gonna skip it. Okay, so now we're done. So lastly, we're gonna check whether DD is the endpoint, which it is true. DD is the endpoint. So there, it's the endpoint. So it can print out the found, which is the path that we found. The final path that we use to get to this endpoint. So it's DD, and then we're gonna print out the maze, which is the output here. So yeah, that's it. That's just it. So as I recap, okay, we will use the queue, okay, and for breakfast search we will search every single possible path, and we combine with the current queue. So for example, left, right, okay, DD, DR, and then we check the valid, we check whether the path valid or not through the valid method. We also check the endpoint, whether we have reached the endpoint or not. If we have reached, then as you can see, it returns true, so it breaks the loop. So yeah, that's it. If I run this, I'm sorry if it's long, but I just want to show you flow by flow on how it works, basically. Okay, so that's it from me. Thank you very much.
Okay, so I actually would like to clarify that I improvise actually the code. So as you can see here, this one, the main algorithm part, I put it in the new method that I create, which called while method. This one is just to display the different kind of maze, just to showcase that. So this is the final code in my report. But for the explanation, I do just like the previous one, which is easy. So this is the what I call the output for 4 maze, and this is the example maze that I used for explanation. So that's it. Thank you. Hope you enjoy.